Good morning all. This is Satish Kumar, Assistant Professor of EC Department. Now let us see the another video lecture series on IAR filter design, that is Butterworth filter. See, the popular methods of designing IAR filter involves the design of analog filter and then converting the analog filter into digital filter. The analog filter transfer function is converted to digital filter transfer function by using either impulse invariant transformation or bilinear transformation. The error function is selected such that the magnitude is maximally flat in the passband and monotonically decreasing in the stopband. The magnitude is maximally flat at the origin at ohm is equal to 0 and monotonically decreasing with increasing ohm. Right? Next one, properties of Butterworth filter. The Butterworth filters are all pole designs. The zeros of the filter exist as infinite. At a cutoff frequency ohm C, the magnitude of normalized Butterworth filter is 1 by root 2. 1 by root 2 means 0.707. The cutoff frequency will be 3 dB less than the maximum value. The filter order n completely specifies the filter. The magnitude is maximally flat at the origin and the magnitude is monotonically decreasing with increasing ohm. The magnitude response approaches the ideal response as the value of n increases. Right? This is the frequency response of analog low pass Butterworth IAR filter. That is defined as, it can be defined as n is equal to order of the filter. With n is equal to 1, the response is n is equal to 2, n is equal to 4, n is equal to 10. The similar response with respect to ohm C, that is nothing but cutoff frequency, we can get the ideal responses 1 by root 2 is equal to 0.707 with respect to ohm. Right? What is mean by impulse invariant transformation? The objective of the impulse invariant transformation is to develop an IAR filter whose transfer function, whose impulse response is the sampled version of the impulse response of the analog filter. The Laplace transform of analog impulse response h of t gives the transfer function of analog filter. Transfer function analog filter is nothing but h of s is equal to Laplace transform of h of t. T is nothing but sampling time period. Therefore, it can be defined as 1 divided by s plus pk is equal to 1 divided by 1 minus e power minus pk of t into z inverse. Next one, the impulse invariant transformation with respect to j ohm and sigma. The left half of the S plane is mapped into the unit circle in the Z plane. The right half of the S plane is mapped into the outside the unit circle in the Z plane in impulse invariant transformation. Next one, bilinear transformation. Bilinear transformation is the conformal mapping. The imaginary of the axis of the S plane is mapped into the unit circle in the Z plane to avoid aliasing of frequency components. In this mapping, the left half of the S plane are mapped inside the unit circle in the Z plane and the right half of the S plane are mapped outside of the unit circle in the Z plane. It is a 1-to-1 mapping. So S can be defined as 2 by t into 1 minus Z inverse divided by 1 plus Z inverse. St is nothing but sampling time period. Right? This is the diagrammatic representation of bilinear transformation. The left half of the S plane is mapped into the unit circle in the Z plane. The right half of the S plane is mapped into the outside the unit circle in the Z plane. It is a 1-to-1 mapping. Right? Now we can going to see the design procedure of digital Butterworth IAR filter. Omega p is equal to passband h frequency in radians per sample. Omega s is equal to stopband h digital frequency in radians per sample. AP gain at passband h frequency, AS gain at stopband h frequency omega s. T is equal to 1 by Fs, which is equal to sampling time. Fs is equal to sampling frequency. Ohm P is equal to passband edge analog frequency corresponding to omega P. Ohm S is equal to stopband edge analog frequency corresponding to omega S. Design procedure. First, we can choose the either the for a given Butterworth digital IAR filter First, we can choose the given sum as bilinear or impulse invariant transformation and determine the specifications of the equivalent analog filter. In case bilinear transformation means ohm p is equal to 2 by t into tan of omega p by 2, ohm s is equal to 2 by t into tan of omega s by 2. In case of impulse invariant, ohm p is equal to omega p by t, ohm s is equal to omega s by t. Next one, we can going to decide the order n of the filter. In case how to find the order of the filter means n1 is equal to 1 by 2 into log of 1 divided by as square minus 1 whole divided by 1 by ap square minus 1 the whole divided by log of ohm s divided by ohm p. Next one, third one, we can determine the normalized transfer function for the analog where n is even, where n is odd. Where n is even means h of s of n means pi k is equal to 1 to n by 2, 1 divided by sn square plus bk into sn plus 1. In case n is odd means the h of s of n is equal to 1 divided by n sn plus 1, pi k is equal to 1 to n minus 1 divided by 2, 1 divided by sn square into bk into sn plus 1. Where how to determine b of k? 2 sine into 2k minus 1 pi divided by 2n. Next we can going to calculate the cutoff frequency. Cutoff frequency ohm c is equal to ohm s divided by 1 divided by as square minus 1 the whole power 1 by 2n. Next one, determine the unnormalized transfer function is obtained by replacing Sn how to replace Sn by S by ohm c in the normalized transfer function. In case of Sn, you can replace your S by ohm c. How to get h of s? Summation k is equal to 1 to n by 2 ohm c square divided by s square plus bk into ohm c into s plus ohm c square. Already we can find out the ohm c square, that is nothing but cutoff frequency. Now we can find out the unnormalized analog transfer function where n is odd means how to replace in the where you can replace same s of n can be replaced by s by ohm c in the normalized Butterworth low pass filter transfer function. Now in case n is odd formula can be already seen in the previous slide. Now we can see by Sn can be replaced by S by ohm c. Therefore, h of s is equal to ohm c divided by S plus ohm c. Pi k is equal to 1 to n minus 1 by 2 ohm c square divided by S square plus b suffix k into ohm c plus ohm c square. Ohm c is nothing but cutoff frequency. Next one, finally we can going to determine the transfer function of the digital filter h of z using the suitable transformation to transform h of s to h of z by using impulse invariant or bilinear transformation. If impulse invariant is employed means if t less than 1 then multiply h of z to t to normalize the magnitude and then realize the digital filter transfer function by a suitable structure. Finally, we can going to verify the design by sketching the frequency response h of e power j omega. H of e power j omega is equal to h of z where z is equal to e power j omega. Now we can see the assessment. Define impulse invariant transformation and bilinear transformation. See here, the objective of the impulse invariant transformation is to develop a transfer function whose impulse response is the sampled version of the impulse response of the digital filter. In bilinear transformation is the conformal mapping. The imaginary or axis of the S plane is mapped into the unit circle in the Z plane. It is a one-to-one mapping. What is mean by Butterworth approximation? In Butterworth approximation, the error function is selected such that the magnitude is maximally flat in the passband and monotonically decreasing in the stopband. How will you choose the order n for a Butterworth filter? N is equal to 1 by 2 into log of 1 by as square minus 1 the whole divided by 1 by ap square minus 1 the whole divided by log of ohm s divided by ohm p. List the properties of Butterworth filter. See, Butterworth filters are all pole designs. The filter n decides the order of the filter. The magnitude is maximally flat at the origin and monotonically decreasing with increasing ohm. Analog filter transfer function is converted into digital filter transfer function by using either impulse invariant transformation or bilinear transformation. define sampling rate. Sampling rate is equal to T is equal to 1 by Fs. That is nothing but which is equal to sampling time. Time is equal to sampling T of S represents your sampling time. Thank you.